Hello, welcome to part 7 of my Common Lisp programming lecture tutorials. My name is Will, and today we're going to be continuing the set of functions that we started in tutorial number 6, which is I'm doing functions as described by a homework assignment for this one class. So I'll put the URL for the assignment in the in the description box so you can follow along, or you can actually just look at them without having to look at the video. So I left off at 2 mdelete, so now we're going to do minsert. Now minsert says write a function that takes as input two items, say A and B, and a list of any structure, say L. The function inserts atom A before all occurrences of the atom B. Excuse me. So let's start it off. Insert, we have atoms A and B, and then we have the list that we're inserting into. We want to call that L just to follow the specifications there. So let's just take the easy case out of the way and go off of that. If we have a null list, then that's technically the list in which we've inserted A's before B's into, because there's nothing there. And this might not seem like the easier case to take care of, but let's take care of this same case. There we had an mdelete, because it actually looks exactly the same. I just copied everything over. Call this insert instead, because if the current element is a list, then what we need to do is we need to recurse into it. And remember, I know that it can be a list because it says a list of any structure, meaning it's allowed to have sublists. So we need to recurse into the car of it, which is that sublist, and we also need to recurse onto the cooter, which is the rest of the list that we haven't done anything with yet. And we need to add those together via cons. So let's take care of the case where they're not equal. And this might seem counterintuitive, but I'm trying to save like the most annoying one for last. So if A and B, or rather if B is not the same as car of the list, then what we just want to do is do as before, just essentially copy it. So cons that with the minsert of the rest of the list. Of course, it would help if I called it with the right arguments, A and B. So now the last case, in which B is equal to the car of the list. So this one is the case where this actually does work, because here we need to return a list that is that has A, then B, and then the minsert of the rest of it, because there might be other B's following this current element. So somewhere in there we're gonna obviously recurse on the tail, and we need to return a list that has A and B, and then add it together with that. So I'm gonna use a fact from lists on how they're constructed, and I think this is a pretty good spot to kind of explain what linked lists or what lists in Lisp are. So if you come from C, this will probably be helpful, but still, if you're from other languages, you can this should still make sense. So in C, when you're creating a new object type, you just do struct and then you give it a name. So here a node, or let's call it cons, because that's what we call them in Lisp. And it has two fields. It has the car that you can think of as just being some data, and it has the cooter. So in C, the car represents, if we had like int data, linked list of ints, and then the cooter is actually a pointer to the next element. So if you have, for example, the list that contains 1, 2, 3, then you have a cons. Your first cons has 1 for its data, then your next cons has 2 for its data, and then 3 has 3 for its data. So what cons does, the cons function, so if I do, for example, cons 0 and nil, it uses this as the car of the cons that you're creating. So you create one of these and you assign the car to be 0 and you assign the cooter to be nil. So in Lisp, the way a normal list is set up is that it's just like this, where the very last cons, the very last node in the linked list, is linked to nil. If we plug this into the REPL, you'll see what I mean. So notice that it returns the list that only contains 0. That's because the first element of this list, or rather the only data of this list, is a cons that has 0 and then nil. So when it prints it out, it essentially stops at nil. Now say we want to form this list of 1, 2, and 3. What we do is this is our first element, and instead of ending the list there, we want to insert another element. So here, what I'm going to do is link it up with another cons that has 2, and link that up with the cons that has 3. And that's our last one, so I'm going to link that up with nil. And like that. If I plug this into REPL, it will give me just that, the list that contains 1, 2, and 3. So, if we want to combine elements like we do here, that's essentially all we have to do. So cons A into the list that contains B, and then that's going to be linked up with this, with the Minsert of the rest of the list. And the reason I don't do a cons here, because this is going to be essentially my last element, is that this call to Minsert, remember that Minsert returns a list that is the insertion of A before B's in that list. So if I do this, we're actually going to be creating a sublist, and I'll show you what it looks like if you do that instead. Let's plug it in correctly first, though. Just double check that. And that's essentially it. We took care of all 4 possible cases, which is empty list, sublist, atom is not equal, and atom is equal. So let's copy that in, paste it. Now let's run his test cases here. And here, if you look, we come up with the same result, which is we just inserted H before that A. You go through here. It's inserting D's before A's, so it sees this A here, puts that D before it. It says Dan. And then D right here, and D right here, and D right here. And as long as everything logically makes sense, that's what matters. Though it isn't wrong to be right with the right answer. So you can run these and verify that they're right. So I want to show you then what happens if you do cons here to end it. So let's copy that. No warnings or anything. It's all good. Oh, let me show you with a simpler case first. Where was it? Yeah, it's somewhere in there. Let me just copy it again. But so this first case is pretty simple because it has no sublists, so it'll be easier to see what's happening. So here what we did, this isn't a very good case at all. Let me change it slightly. So I'm going to put the A right here in the middle. So notice that it did its job up to A. So it inserted that H right before A. But then after that, everything after is essentially like bunched up in a list. And that's because we grouped this list, we essentially put it in another list by consing it with nil. So anytime that so for example, if I had another A right here, it would actually create yet another list afterwards. And it all makes sense as to how you're linking up everything. Let's change that to the correct results or answer. Another way to go about this, and I don't want to spend too much time on it, but another way to go about this line, if you don't like the double cons, you could always create a new list that has A and B, and then you could append that to the Minsert of A and B executor list. This is the alternative solution to it. I don't like this approach because it's creating a list here for no reason. From an efficiency standpoint, I really don't like it because I come from C. So I don't like the fact that it's creating a new list, and I don't like the fact that it's having to append them into yet another list. So efficiency standpoint, do the other one. Alright, let's see how much time I have. Oh wow, that spent way too much time. Let's see if we can do this one before. Okay, I think we can maybe squeeze this one in. Let's get rid of that. Alright, so in this one we've taken a list that has only sublists, and it counts the number of atoms in each sublist. So in this one we get to use helper functions. So, easy case out of the way. If the list is null, then that is the list that contains the blah 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 blah. It all makes sense if you think about it. So otherwise we have we have a sublist here. So we need to find out how many atoms there are in this sublist. This is a great time. I'm going to write T there because those are the only two cases. Either we have something or we don't. So we need to replace that current one. So instead of saving that, so instead of doing this, instead of using that element, we're going to replace it instead with the number of atoms in that sublist. So I'm going to go ahead and say, call another function called atom count. That's not how you spell atom. And that function is going to count how many atoms there are in that sublist. And then I'm going to put that together with the S count of the rest of the list. Format this nicer. So what I've done is split my problem so that it's a lot easier to manipulate. So now in atom count, I have a list of any structure. I have a list of any structure, such as, for example, here, and I need to find out all the atoms that are in that list and count them. Oh, geez, not enough time. Oh, actually, no, I did get the increase in video times, so I can actually post as long as video as I want. I think, sort of. It's longer than 15 minutes, which is what matters. So, atom count. It needs to go away. It needs to count how many atoms there are in this list, and this list can be of any structure. So, by technicality, the number of atoms in a null list is 0. Now, the number of atoms in a list, So otherwise we at least have one thing. So what we can do is, if the car with this list is an atom, then we can count 1, right? But then we also want to add that to the number of atoms in the rest of the list. So what we can return is add 1 to the atom count of the rest of the list. So we're counting this one as well as the rest of them in the tail of the list. Otherwise, it is a sublist. So what we need to do in this case is we need to count how many atoms there are in that sublist and add that together with the number of atoms there are in the tail of the list. So just as easy as I say it, we have a function that returns how many atoms there are in the list. So we go atom count on the car of the list. So that tells us how many atoms there are in that sublist, and we add that together with how many atoms there are in the rest of the list. And that's it. Simple as that. Tells us how many atoms are on the list. And that is it. Let's load them here. By the way, a word of caution when you copy paste. Oh, so cut that out. When you copy paste into, as you're doing right now, or as you see me do right now, is that if you have commented lines, it might mess up like the input. So I typically avoid it, but here I know it's going to be right. But just to be sure, if you get any weird errors where like it's waiting for more input, it could have been that the commented, like before I had this, but it could be commenting more than you think when you copy paste it because of formatting stuff. Long story short, just use load is better. But I was lazy and didn't want to switch the desktop. Anyway, so paste that in. We can actually test them individually. We don't need to, if we run into any issues, it's a lot easier to nail them down if we know if things are working right. So atom count BC, that should give us 3. 3, cool. Let's give it nil. It's always a good test case. So now we need to look at a list of any structure. So let's put B inside of double parentheses here. Still 3, which is good. Let's put a D here. 4. Awesome. That's thorough enough for me because I know for a fact that it works. So that's it for you. So now S count. Now that we know that atom count is working, we can rely on it to be correct. So if there's any faults with our code, it has to be an S count. And that's a general thing, not just in Lisp. In general, you want to separate your problems, so that way it's easier to find the issues. So S count of, so it needs to be a list that contains sublists. So let's give it this. So 111. So here if we give it, for example, E, in that first sublist, I created another sublist that has E in it. Now it says that there's 2 atoms in the first one, and 3 atoms in that second one. And it makes sense because all we're doing is just instead of at every single element of this list, we're just turning it into the atom count of that element. And that's a pattern that we can express in mapping, and I'll go over that in the next video as soon as I finish these things. So seeing as I have a bigger limit and I've already gone over my previous limit, I'm going to go ahead and go for the last function right here, which is SMax, or M maximum. So it says write a function M maximum that returns the greatest number in a list containing just numbers. Okay. I think this one is a little tricky. Yeah, it is a little trickier with what you have to do. It's not too bad. but it's still kind of a annoyance. So here I'm going to go ahead and introduce if you remember, the let special operator allows you to define local variables. So here I can do like let var, or let var equals 0 to initialize it to 0, and I can use, you know, any number of stuff. And here I can see like var, and I'll return var. Alright, so I'm going to be using that to solve this particular problem. Mostly because it has some annoyance issues. So, the maximum in a list that contains only, so in an empty list, this one is actually not very well defined. We can make because if you have an empty list, what is the greatest value in it? If you say 0, then it's kind of iffy, you know, because 0 wasn't actually in the list. But for my purposes, I'm going to assume that all the numbers are non-negative, so I'm going to use 0 for that. And that's kind of a choice you have to make, because in the specification they weren't clear on what happens if you're given an empty list. That's not something that they specified, so you kind of have to make a choice there, whatever makes it easier for you. So if it's not empty, that means that there's actually something in here. Then we need to find out, do we want to use the current value? Is it greater than anything else in the list, or do you want to use something further down the list? So, put a T here. So what I'm going to do is we know we have at least this element. So I'm going to create a new variable called RestMax, and that's going to be the mmax of the rest of the list. Because what that's letting me do is that now RestMax is the greatest value in the rest of the list. So now what we can do is, if the current value is greater than the RestMax, then what we can do is we can just use this value as the return. Otherwise, we just use RestMax. Does that make sense? Where am I asking? But that should make sense in that we're looking at the rest of the list and we're finding out what is the largest value in that list. And we're saying, well, is it larger than the current value? If the current value is greater, then we want to use that because it's better than anything else in the rest. Otherwise, we want to use that value that we got from the rest. And that's pretty much it. Close the let, close that, and close that. So this function looks uglier with correspondence to the other ones, and hopefully in the next tutorial I'm going to go ahead and go through this again when we learn about higher order functions and closures and some other fun stuff like that. It'll be easier with those. But here, the purpose of the let, you could avoid using it by, instead of using RestMax, you use this. So let me get rid of the let. So instead of RestMax, I'm going to use the maximum of the rest of the list. Same thing here. But the problem is that, imagine you have like a really long list. Then you're using m maximum, which needs to go through that entire list to compare here, and then you're using it again here instead of just saving whatever value you got from it originally, which from an efficiency standpoint is kind of like, ugh, I don't like that at all. But I mean, if this reads better, that's the purpose of these tutorials, is to just teach you to do that. And actually, since we have it in this form now what we can do is just put this straight into the cond. So if it's true that this value is greater than the rest of the list, then what we want to use is the current value. Otherwise, we want to use the rest of the list. That way it looks a little nicer. Still not very nice though, because we're calling this twice unnecessarily. But this is the cleaner way it looks like for now. Alright, I'm gonna end it there. That's the last one for there, and I'm gonna hopefully start on my next tutorial. Goodbye.